This is your 5.1 notes. This is the first section is entitled Exponential Functions. Now, exponential has that root word exponent. So these functions deal with exponents, and the exponent is going to be the variable, is what we're going to see. Now, just to kind of give an illustration here, I've got x and y pairs. And notice x is just 0 through 9. But look at the pattern in y. If you can see it, every time we move from one y value to the next, we multiply by 2. So all the way through here, as I go from one to the next, I'm always multiplying by that same number, 2. Alright, all the way through. Now, notice up here, we haven't multiplied by 2 from this first thing. The pattern hasn't been developed. But from here on, we keep multiplying by 2. So how many times have we multiplied by 2? From here to here, we've multiplied by 2 once. From here to here, we've multiplied by 2 twice. Here to here, we multiplied by 2 3 times. Okay, so what's doing that? What's going on here? The x value is keeping track of how many times we multiplied by 2. We haven't multiplied by 2. We multiplied by 2 once. We've multiplied by 2 twice. We multiplied by 2 3 times. All right, and so on and so on and so on. All right, another thing that's going on is this is 2 to the first power. This is 2 squared. This is 2 to the third power, or 2 times 2 times 2. 2 to the fourth power, and so on. So again, that x value is keeping track of how many times we've multiplied by 2 as we go along here. So this is the equation, y equals 2 to the x, or in function notation, f of x equals 2 to the x. Okay, meaning that we plug in an input, and the input is now the exponent. Alright, that's the important thing for you to understand for exponential functions. The input is the exponent. Alright, in exponential functions, we call the number, or the whatever this is down here, we call it the base, and then obviously again x is the exponent. Alright, so base and exponent are the two main parts of an exponential function. Alright, here's a definition of an exponential function. B is a positive real number, so no negatives. And the function f of x equals b to the x is exponential. B is called the base of the function, and x is the exponent. So just some examples of exponential functions. Okay, all we need is a positive real number. So I could take something like y equals 3 to the x. Okay, or if I used function notation, f of x equals 8 to the x. Okay, it doesn't have to be whole numbers. Okay, we could have something like f of x equals 3.21 to the x. Right. F of x equals 1/2. Okay, it doesn't have to be bigger than 1. Okay, it just says it's not equal to 1. So positive, but not bigger than 1, 1/2. That'll work. 1/2 to the x. Alright, and then later on we'll see things like where the x, the input, gets multiplied by something. So we might see something like 5.2 to the negative 3x, something like that. As long as the variable's in the exponent, right, then we're dealing with a exponential function. Alright, now this, I don't like this picture. This is from your book. I don't like this picture that much because it looks like these are both there at the same time, but they're giving you two different types of examples. So I'm going to color in this second one red just to illustrate there are two scenarios going on here. Okay, so this is the same equation for both. Y equals b to the x. The x-intercept is none. The x-axis is what we call horizontal asymptote. So the x-axis is never touched. Alright, and that's what we mean down here. A horizontal asymptote is the x-axis. That means as these graphs go towards the end, either negative infinity or positive infinity, the graph approaches the x-axis, but it never crosses it, never touches it. So that's what we mean by a horizontal asymptote. Alright, y-intercept 0, 1. So that's this point right here. Is always going to be our y-intercept of an exponential function. Domain, all real numbers. We can plug in any number into this, as long as b is a number bigger than 1. Okay, a positive number. Bigger than 0. And the range is all positives. Alright, all the graph takes place above the x-axis unless this thing is shifted. That'll be our range. Alright, and then this is the important part. This is why we have two graphs. It's increasing, that's the red, if b is greater than 1. So if we're talking about 5 to the x, 3 to the x, 2.1 to the x, like we've been seeing, they're all going to have this same basic shape where it's always going uphill, left to right. Alright, but it's decreasing, that's the blue one. Alright, if that number 1 is between 0 and 1, a proper fraction, or if we raise it to the negative x power and b is a positive number. Okay, so that's like a negative exponent. So just for example, I've got two different types of functions in here. One is y equals 3 to the x, one is y equals 0.5 to the x. So these are two that I have from back here, this first one and then this one right down here. So when I graph these, notice I've got the second one in bold so we can distinguish who is who. When I graph these, there's the 3 to the x first, alright, and then here is the 1/2 to the x. Alright, so again, that's what this is telling us here. There's the 3 to the x, so that's bigger than 1, so it's going uphill. Here's the 1/2 to the x, so that's between 0 and 1, so that's going downhill. Alright, now notice here that it says b to the negative x. So if I did 3 raised to the negative x power. Again, did that one in bold so we can distinguish the two. There's the 3 to the positive x coming first, and then here comes the 3 to the negative x in bold coming down on the other side. Okay, so a negative exponent will flip that thing around the y-axis, which is what we've seen before. Okay, so that's what's taking place here. That negative input, when we negate the input, we flip around the y-axis. So that's what's going on there with the graph. But anyway, both of these, either one of these, will cause this thing to be decreasing. Alright, if your base is between 0 and 1, or if your exponent is negated and b is greater than 1, then we flip around that y-axis. Alright, now this is transformations of functions, just like before. I don't know if you can see it very well. This says y equals 3 to the x, and this says y equals 3 to the x minus 4. Okay, so this is a shift to the right 4 units. So all those different things that we talked about in the previous chapter still holds here. Okay, this is y equals 3 to the x. This is y equals 2 plus 3 to the x minus 4. Alright, so that x minus 4 shifts it to the right 4 units. And then the plus 2 shifts it up 2 units. Alright, and now that asymptote is at 2 rather than the y-axis. Okay, it crosses at 1 here. Okay, that's taking place 4 units to the right, 2 units up. So 4 units to the right, 2 units up. Alright, that's taking place at 3 here. Alright, 4, 3, that is. Alright, that's the new location of that that y-intercept. Alright, it's gone over 4 units and up 2 units. just like every point on the graph has. Alright, and then this one, 5 times 3 to the x. Just like before, if we multiply the output times a number, it's a vertical stretch by a factor of 5 in this case. So again, it's like we grab the graph and pull it upward. So notice this had 0, 1 as its old y-intercept. Now this has 0, 5 as its y-intercept. Okay, because of that 5 that we multiplied it by down here. Alright, so just exact same, the thing I want you to understand here is the same transformations as before. So nothing's different, it's just we're applying it to a new type of function. Alright, now this is a really important thing for this section. Exponential growth models. Alright, so they look like this. Alright, we've got that thing out in front that we're multiplying by. And there's our base, just like before. And then k is some type of a number that we're multiplying the input by. Okay, so we're multiplying the output and the input. Alright, a and k, b, everything. B is a bigger than 1, so it can be growth. Alright, k is also bigger than 1, or bigger than 0, so it can be growth. Alright, remember if we go back, k is in the place where that negative sign was. So if k were negative, it would go downhill, wouldn't grow. So that's why k has to be positive for this thing to grow. Alright, again, no x-intercept. The y-intercept is 0a, whatever a is. Okay, so there's a on the y-axis. Domain's all reals, range is y is greater than 0. Okay, so the next couple of examples will deal with exponential growth models. Alright, total principal income in the United States in billions for selected years from 1960 and projected to 2018 can be modeled by this, with x equal to the number of years after 1960. Okay, so what we got to understand here is stuff like x equals 1 means 1961. Okay, x equals 40 means the year 2000. Okay, so we just got to understand how we have to adjust this, how we have to use this function. Alright, what does the model predict the total U.S. Personal income to be in 2014? So to get that, go to your calculator. Alright, I've got typed in 4.924, alright, parentheses 1.07, and then raised 2, and then x is what we got to figure. So what does the model predict for 2014? That's 1960 from 2014, so you can either literally type it in 2014 minus 1960, or that would be our number, or you can do 2014 minus 1960, get that number, 2014 minus 1960, get that number, 54, and then plug that in. So 492.4 times 1.07 raised to the 54 power. In both cases we get the same number. Alright, so this is in billions of dollars. So that would be 19,012 billion. Alright, 0.62311. Or that's equivalent to 19.0 trillion. Okay, 1,000 billion is a trillion. All right, part B. Graphically determine what year during which the model predicts the U.S. personal income will reach 28.5 trillion. Okay, so we're not there yet. So if we want to do it graphically, we need to put this into our calculator. So 492.4 parentheses 1.07 to the x power. Right, that's exactly what this says. Right, now I'm going to change my window. I'm going to make it go from 0. This goes up to 2014. Let's make it go past that. So 40 meant 2000. So that means 54 would mean this. So let's make it go to 100. Alright, we'll make our scale go in 20s. Alright, a y minimum doesn't need to be bigger than 0 because that's the horizontal asymptote. And then the max, this was 19,000. We need it to go to beyond 28.5 trillion. Alright, that's 28,000. So let's make it go up to 30,000. Alright, and we'll do it in 10,000s. Let's do it in 5,000s. Alright, let's look at our graph and see if we can see that intersection in the window. So there's our exponential growth. Alright, exponential growth kind of looks like a part of a parabola. Oh, I'm sorry, I didn't put in the second part of it. So to graphically find the intersection, we need to put in 28, not 0.5 trillion, but 28,500. Okay, remember this is measured in billions, not trillions. So 28,500 billion is a 28.5 trillion. So that's what we're looking for here. So there's the intersection. Find the intersection, option 5. First curve, that's it. Second curve, that's it. And our guess is right there. Alright, so 59.98, around 60 years until it gets to 28.5 trillion. So 60 years after 1960, which is approximately 2020, the total U.S. income will reach 28.5 trillion. Alright, I'm going to give you an example from your homework. This is 5.1 homework, problem number 9. The reason I'm giving you this one is radioactive decay. Alright, we have a negative exponent, so that means it's going downhill, if you remember from the earlier notes. So it also has e as this base. Now e is a number just similar to pi. If you go to your calculator, if you look above the division symbol, the second function there is the e number. So it's this number, it's similar to pi in the fact that it repeats. I mean, it never repeats, it never terminates. It just has a pattern that goes on forever and ever and ever, or it never falls into a pattern, that is. So anyway, if e is being raised to a power like it is here, we won't use this one. We'll use this one over here, e to the x power. Okay. If we do that one, notice it gives us the e with the caret already and everything ready to go. Alright, so for this particular scenario, t is the time in years that the isotope has decayed. Initial amount present is 500. That number out front is always your initial amount before the decaying process starts. Alright, how many grams will remain after 5 years? That literally means just plug in 5 where that t is. So 5,000 or 500 second e to the power of, and then type in this number, negative 0.02844 times t is, in this case, 5. I gotta clean this up because I put in too many decimal points. Alright, so that's just plugging in 5 where the t was. So 433.72. Alright, part B says graph this function for 0 to 100 and choose the correct graph below. Notice they're giving us the both the x and y scale there. So if I plug this in, alright, notice I used x where they had a t. Alright, that's fine to do that. And I'm going to use the window they tell us to. So from 0 to 100, I already got that. Alright, and then from 0 to 900 for the y-axis. Alright, and looks like they've got those in hundreds. And then here it looks like they got them in tens. Alright, and now we're just looking to see which one of these graphs match up with what I see on my calculator. So obviously it's not this one. Definitely not this one. So it's got to be B or D. And if I hit trace and plug in 0, so I can get the initial value. Remember, the initial value was 500. It looks like only, if I blow this one up, that doesn't have an initial value of 500. Looks like only B has that initial value of 500. Alright, so B is my choice. Alright, so it's got to be going downhill. Right, these two go downhill, but it also has to be starting off at the right place. Alright, part C says if half-life is the time it takes for half of the amount, or half of the initial amount to decay, use the graphical methods to estimate the half-life. So what that means is half of the initial value is 250. So since the initial value is 250, we're going to type in 250 and find how long it takes to get down to half. Okay, so I've graphed it in there. There's the 250 line. There's where they intersect, and that's what I'm looking for. The x coordinate of that intersection is the answer down here. So intersect, first curve, second curve, guess, try to get it close. Alright, if you only have two things that you're intersecting, you always just hit enter for first curve, second curve. So 24.37 roughly is our half-life. Alright, so I wanted you to see this example. Just use that second LN button, e to the x, to be able to plug in this e number on there.